The theory of linear model is one of the most elegant parts of the whole mathematical statistics. If done correctly, textbooks on linear regressions and linear models in general typically look like what is shown on the screen. Namely, seas of algebraic drudgeries riddled with sigma notations. What we will demonstrate in this video is that a lot of these algebraic messiness are artificial, and hence the title of this video, which is obviously a homage to Sheldon Axler's Linear Algebra Done Right. Fantastic book, by the way, and it's free in case somebody doesn't know. So the plan of this video is to present the usual theory of linear regression purely geometrically. There is not a single complicated formula in our exposition. And at the end, we will see why this diagram on the screen is the right way to think about linear models, and not the usual scatter plot superimposed with a least square line. Let's go. Suppose we have these 3 points, 1, 1, 2, 3, and 4, 4. Can we, based on the data, conclude there is a linear relationship between the variables x and y? If we use the linear regression feature provided by Desmos, we can add a least square line, and the R-squared statistics turns out to be 0.8622. So the R-squared statistic is a goodness of fit metric. The R-squared is always less than 1. The closer R-squared is to 1, the stronger the linear relationship. So, to the untrained eyes, this may appear as strong evidence for the linear relationship. But as we will see in this video, this so-called trend, and trends that are more pronounced than this one, for the same sample size, has a roughly 25% of appearing purely due to random fluctuations. So how do we approach the question that whether a linear relationship is significant? Well, we can certainly fit a straight line as much as possible to all these points. We said as much as possible because typically not all the points lies on the same line. And then we're going to fit a horizontal line, that is a linear relationship with no trend in x. Any variation in y is purely random. Then we compare the goodness of fit in these 2 methods. It is obvious that if we allow the straight line to have non-zero slope, the goodness of fit automatically increases. So that's not really saying much. What matters is the amount of increase in goodness of fit, and the goodness of fit in the 2 situations, as well as their difference, can be visualized cleanly as such. As we will explain, to do so, we need to go to a higher dimensional space, in 3D in this case. So this is the situation. The meaning of these vectors will be explained later. But for now, let's just focus on this right triangle in space. The right triangle with yellow, purple, and red sides. We can vary our perspective to check this actually looks like a right triangle. Here it is. It does look like a right triangle. So, what does this mean? The size of the red side, that is the hypotenuse in this right triangle, is the goodness of fit when we do not allow any trend. The size of the purple side is the goodness of fit when we allow trends in the model. By the Pythagorean theorem, the difference between the squared length of the red side and the squared length of the purple side is the squared length of the yellow side. So the yellow side represents the difference in the goodness of fit between the 2 approaches. As we can see, the yellow side, albeit greater than the purple side, it is not significantly so, meaning not like several magnitude bigger. So in this case, it tells us that the goodness of fit between the 2 approaches, namely allowing trend versus not allowing trend, is not that big. So the so-called trend in the data have a good chance of just being random fluctuations. And now we need to formalize things to make this discussion more precise. For the ease of visualization, we will discuss linear regression with 3 points, but the idea generalizes almost verbatim for arbitrary dimensions. So, given 3 data points, x1, y1, x2, y2, and x3, y3, under what circumstances is a non-trivial linear relationship between x and y supported by the data. The linear relationship reads yi equals to beta naught plus beta 1 times xi plus epsilon I. So that is to say yi has a deterministic component, beta 0 plus beta 1 xi, and plus a random noise. The random noise, epsilon I, are IID, normal 0, sigma squared. I equals to 1, 2, and 3. And by non-trivial, we mean that the slope is non-zero. Okay. If the slope is 0, then y is purely random, meaning it has nothing to do with x. So in this model, which we call 1, the parameters beta naught, beta 1, and sigma are all unknown constants. The predictor x, that is x1, x2, and x3, are treated as deterministic. So there is no randomness to the coefficients, the x, and the sigma. Okay. And for each I, yi is a random variable because it's a fixed number plus some noise. And for little y, and we treat the little y's, little y1, y2, and y3, as realizations of the random variable big yi. To answer a question, we follow the main idea as follows. We're going to fit the data as much as possible to the model 1. First, with no additional assumption. And second, with the additional assumption that beta 1 is 0, i.e. y is purely random. We fit these two models separately and compare their goodness of fit. If the goodness of fit difference is small, that means the linear relationship is insignificant. And for that reason, we need a metric for goodness of fit. And that's the least square criteria. For a given line, we can plug in the xi's and get the corresponding y coordinates. And then we just calculate the difference between the y coordinates given by the straight line and the actual yi's, the actual observations. And the resulting differences are called the residuals. We then square all the residuals and add them all together. And this is the residual sum of squares, which we denote as S of beta 0 and beta 1, because S depends on the choice of coefficients. So we wish to minimize this quantity, and the resulting coefficients, beta naught and beta 1, are chosen as our estimates. And the actual minimum value of S is the goodness of fit of the model to the data. And this is a usual visualization of least square regression. A scatter plot with a least square line superimposed on it. But now we're going to introduce some vector notations and see geometrically what this S is about. The vector big Y is big Y1, big Y2, big Y3, and the vector 1 is 1, 1, 1, and the vector X is X1, X2, X3, and the vector epsilon is epsilon 1, epsilon 2, and epsilon 3. Remember, big Y is the random response, and 1 and X are deterministic vectors. Epsilon is the vector of random noise. So here Y and epsilon are random, 1 and X are fixed. And because 1 and X is fixed, they determine a plane in the space R3. That is the span of 1 and X. This consists of all the linear combinations of 1 and X. And we denote this plane as M. This plane M through the origin is a subspace of the 3D space. I just referred to M as a plane. By that, I already made an assumption. That is, 1 and X are not in the same direction. If 1 and M are in the same direction, then the subspace M collapses to the line spanned by 1. It's just a one-dimensional subspace. So in order for this to be a plane, I already assume that X and 1 are not linearly dependent. So going back to our model, this is just the component form of the vector relation. Vector Y is equal to beta naught times the vector 1 plus beta 1 times the vector X, and then plus the vector epsilon. And this is completely geometric. Beta 0 times 1 lies in a one-dimensional subspace spanned by 1. Beta 1 times x lies in the one-dimensional subspace spanned by x. And their sum is the mean response, which we call mu. Obviously, mu lies in M. So the mean response vector always lies in the lower dimensional subspace of R3, regardless of the values of the coefficients beta naught and beta 1. And now we just perturb this mean response vector by a random noise epsilon, which is the red vector. And the resulting sum of mu and epsilon is a random response vector y. Because of the randomness in epsilon, y does not necessarily lies in the same plane as mu does. The sphere on the diagram indicates that epsilon satisfies a rotationally invariant distribution. It's because the components of epsilon 1, epsilon 2, and epsilon 3 are IID normal distributions with zero mean and the same standard deviation. We discussed on this channel multiple times that this kind of random vectors, that is, if we rotate the coordinate axes, which are mutually orthogonal, then the components of the vector epsilon with respect to the new axes are still IID normal 0 sigma squared. And this will play a huge role when we discuss statistical inference about linear models. So here are a few key observations from this diagram. If 1 and x are linearly independent, the subspace M is a plane through the origin. If 1 and x are linearly dependent, namely if x1, x2, and x3 are equal, then M collapses to a line through the origin. That is, M is equal to the span of 1, which we denote as this double strike 1. So the original model 1 now reads in vector form, big Y equals to mu plus epsilon. The random response is a mean response plus a random noise vector, where mu is in the subspace M, and the epsilon follows a normal distribution with zero mean, and sigma squared times I3, where I3 is the 3 by 3 identity matrix. If 1 and x are linearly independent, then the true coefficients, beta 0 and beta 1, are the coordinates of mu relative to the bases 1 and x for M. And if 1 and x are linearly dependent, the coordinates are not well defined. So this is a geometric illustration of the model. That is how we describe random response big Y. But what about our data? What about the observed Y's? So we retain the vector 1, vector x, and the resulting span, the subspace M. Here we also assume that 1 and x are linearly independent. We now introduce the observed response vector y with components little y1, y2, y3, and the e vector. The e vector is the little y minus beta naught 1 minus beta 1x. Of course, this depends on the coefficients beta naught and beta 1. And the function s we defined earlier, the residual sum of squares, is now a squared length of a vector, is the squared distance between y and an arbitrary point in the space M. We wish to minimize s. And by Euclidean geometry, we simply choose the foot of perpendicular. That is the fitted response, the vector mu hat. Be careful that this mu hat, the fitted mean response, has no a priori reason to equal to the true mean response. This is just another vector in the plane M. And now, after mu hat is found, we can find its coordinates relative to the bases 1 and x for the subspace M. And the coefficients, or the coordinates, beta naught hat and beta 1 hat, are the estimated coefficients in the least squared line. To summarize, S is a squared Euclidean distance between y, a point in R3, and a point in the subspace M. By Euclidean geometry, the closest point on M to y is the foot of perpendicular, PMY, of y onto M. This is the estimated response, mu hat. And we write mu hat equals to PMY. If 1 and x are linearly independent, The estimated coefficients, beta 0 hat and beta 1 hat, are the coordinates of mu hat relative to the basis 1x for m. And if 1 and x are linearly dependent, the estimated coefficients are not well defined. And this diagram also explains a concept that causes a lot of confusion. So what does the degrees of freedom mean? The degrees of freedom is nothing but the dimension of the subspace in which the vector lives. The vector y lives in the ambient space, R3. So the observed response has a degree of freedom of 3. You can think of it as all of its components, y1, y2, and y3, are unrestricted. So it has maximal degrees of freedom. And the fitted response, by its own very nature, lies in the subspace M. So it has only 2 degrees of freedom. And the residual vector E, being always perpendicular to the plane M, has only 1 degree of freedom. E lives in the orthogonal complement. M is 2-dimensional. The full space is 3-dimensional. So E can only lie in the subspace of 1 dimension. And now the original question can be reformulated in terms of vectors and subspaces. The original question is there a linear relationship between x and y? If y is purely random, that means beta 1 is 0. So therefore, the true mean, mu, lies in the subspace 1. So 1 is not only a subspace of the whole R3, it is also a subspace of M. So now the question reduces to testing the hypothesis. H0, the null hypothesis, that says mu lies in the subspace 1, versus the alternative hypothesis HA, that says mu indeed lies in the full subspace M. So the original model says that mu lies in the 2-dimensional subspace. And H0 here goes one step further. It says mu not only lies in M, it is in fact lies in the subspace of M, the subspace spanned by the vector 1. So that's the question we're now focusing on. So to answer this question, we must have 1 and x linearly independent. Otherwise, the space M collapses to the space 1, and the null hypothesis and alternative hypothesis became 1. And this is very intuitive, because if x and 1 are linearly dependent, that means x has identical components, which means in the original data set, the x are all the same. How can I tell whether x influences y if x are all the same, right? In order to perform a hypothesis test, we need a test statistic. So the test statistic needs to have certain properties. First of all, it needs to depend on the data alone, because if the test statistic function involves unknown parameter, you cannot calculate it. That's for one. And second, we need the test statistic to measure the discrepancy between the two hypotheses. Or equivalently, the test statistic measures the deviation of the data from the null hypothesis. It is a measure of evidence. And we also need D, the test statistic, to follow a parameter-free distribution under H0. So this goes back to the basics of hypothesis testing. We wish to test H0, so we're going to assume H0 is true and see whether there's evidence against it. The evidence against it is measured by the test statistic D. If, given our observation, D is some sort of extreme value that is highly unlikely to observe, then we conclude that H0 is probably false and we reject it. So now our goal is to construct such a test statistic. And here comes the most important diagram of this video. We will explain every element of it in detail. So M is a subspace we introduced earlier. 1 is a span of the vector 1. O is the origin. And now we have this mean vector mu, which is beta naught times 1. Why is the true mean a multiple of 1? Well, this is because we assume the null hypothesis. Remember, when we construct a test statistic, we wish to find its distribution under the null hypothesis. Epsilon is still a random perturbation of the mean response, and epsilon follows a rotationally invariant Gaussian distribution. The vector sum mu and epsilon is the data vector y. Or in the diagram, mu is the vector OB, the random noise vector is the vector BA, and the random response vector, big Y, is the vector OA. And now we're going to do a bunch of projections. First, we introduce a notation, PM perpendicular, the identity operator I minus the projection operator PM. So PM perpendicular acting on a vector takes the perpendicular component of that vector relative to the space M. And here we can see from the diagram, PM perpendicular acting on Y is the same as PM perpendicular acting on mu plus epsilon. Right? This is nothing but the representation of Y. Y equals to mu plus epsilon. And now by the linearity, we get PM perpendicular mu plus PM perpendicular epsilon. And because mu lies in M, PM perpendicular mu is 0. So overall, we have PM perpendicular Y equals to PM perpendicular epsilon, which lies in the orthogonal complement of M. That is, in a diagram, the one-dimensional space that goes along the vertical direction. We're going to project the random response vector Y onto the plane M. This is equivalent to fitting the model with trend using the least square method. Point A drops a foot of perpendicular onto the plane M at the point C. So by construction, AC is perpendicular to all the lines or vectors contained in M. Next, we draw a perpendicular of A onto the line 1, and the foot of perpendicular is the point D. We then connect the points B and C and C and D. So by the geometry, the vector epsilon is the vector BA, which is equal to the sum of the vector BD, the vector DC, and the vector CA. And epsilon follows a spherical normal distribution. So if we can show that the vectors BD, DA, and CA are mutually orthogonal by the rotational invariance of the spherical Gaussian distribution, we immediately have the signed lengths of these vectors, BD, CD, and CA, are IID normal 0 sigma squared. So let's go and prove the mutual orthogonality. So first, let's see which pairs are clearly orthogonal. We have CA orthogonal to the plane M. That means CA is perpendicular to all the vectors in M. So for that, we have CA perpendicular to BD and CA perpendicular to CD. Let's say that again. CA is perpendicular to BD and CA is perpendicular to CD. And now it just remains to show that BD and DC are perpendicular. Here they are, BD and DC. And to do that, we use our construction that AD is perpendicular to the line 1. DC can be written as AC minus AD. BD dot product with DC is BD taking dot product with AC minus BD times the dot product with AD. Claim that the three vector components are IID normal 0 sigma squared. It suffices to show that the three vectors are mutually orthogonal. By our construction, CA is perpendicular to M. DA is perpendicular to 1. So immediately, BD is perpendicular to CA. DC is perpendicular to CA. So it remains to show that BD and DC are perpendicular. And to do that, we use a dot product. BD dot DC equals to BD dot AC minus AD. BD is perpendicular to AC. BD, because it lies in M, it is perpendicular to AC. And the second dot product, BD dot AD, is also 0, because by construction, AD is perpendicular to the line 1. So BD dot AD is also 0. And therefore, BD dot DC is 0. This proves that the three vectors, BD, DC, and CA, are mutually orthogonal. And therefore, by rotational invariance, BD, DC, CA, these signed lengths are IID normal 0 sigma squared. So this claim we just proved, immediately gives rise to the so-called F statistic. The triangle ACD is a right triangle in which the angle ACD is the right angle. And therefore, by the Pythagorean theorem, AC squared plus CD squared is equal to AD squared. So AC squared is the minimized residual sum of squares for the model in which there is a trend. And AD squared is the residual sum of squared in which we do not allow any trend in our least square model. The length CD squared is improvement in the least square estimation by allowing a trend. To say that again, since the triangle ACD is a right triangle with the angle ACD equals to 90 degrees, by the Pythagorean theorem, AC squared plus DC squared is AD squared. And we know that AC squared is the perpendicular of epsilon onto m squared, which is equal to the perpendicular of y onto m squared. And AD squared is the perpendicular of epsilon onto the subspace 1 squared, which is equal to the perpendicular of y onto 1 squared. So therefore, the difference in the goodness of fit between the two models is DC squared, the difference between the two square lengths. And here we have an analysis of variance table, aka ANOVA table. So this is the meaning of analysis of variance. It's just a Pythagorean theorem. The usual analysis of variance identity shown in most textbooks looks like an algebra coincidence, but it is not a coincidence at all. It is purely geometric. The F statistic in this case is the difference between the residual sum of squares, i.e. the length of DC squared, divided by the residual sum of squares of the full model, that is AC squared. A, the letter A, the tip of the red vector is hidden because the diagram is a little bit large. In general, it should be DC length squared divided by the degrees of freedom of DC, and then divided by AC length squared divided by its own degrees of freedom. And as we have shown, that DC and AC are orthogonal and therefore independent, and each follows a sigma squared times a chi-square 1 distribution. The F statistic in this case is just a ratio between two chi-square distributions with 1 degrees of freedom. And this is exactly our test statistic. The F statistic is defined as DC length squared divided by AC length squared, which is equal in distribution to U squared over V squared, where U and V are IID normal 0, 1 random variable. And the distribution between two normal 0, 1 random variables is actually well known. We made a video a while ago. It's a Cauchy distribution. So this F statistic follows the distribution F11. 1 and 1 stands for the degrees of freedom of upstairs and downstairs. So F11 is equivalent to the Cauchy distribution squared. To find its CDF, a cumulative distribution function, that x follows the Cauchy distribution and define y equals to x squared. We can find the CDF of y really easily and then its critical value. So we know under what circumstance should we reject the null hypothesis. The Cauchy distribution has a CDF of 1 over pi arctangent of x plus 1/2, and y is x squared, so the CDF of y, which is defined as the probability of y less than or equal to little y for y positive. This is equivalent to the probability of x squared less than or equal to y, which is equivalent to the probability of x greater or equal to minus the square root of y less than or equal to the square root of y. So we can just plug in the two endpoints of the interval, minus square root of y and the square root of y, into the CDF of Cauchy. Simplifying, we get 2 over pi times the arctangent of the square root of pi. So if we set this probability, the cumulative probability, to be p for some p between 0 and 1, and we have 2 over pi times the arctangent of the square root of y equals to p, and this gives the critical value, the tangent of half pi p squared. That's the p quantile for the distribution F11. Let's just plug in a number, say p equals to 95%, because that's the most common value for hypothesis testing. and see what this value is. And turns out that this critical value at 95% is quite large. It's 161.45. So what does this mean? This gives us a decision rule. If the F score is greater than the critical value, F11, at alpha level, which is the tangent of pi times 1 minus alpha over 2 squared. Remember, rejecting H0 means there is a non-trivial linear relationship between x and y. So if we use alpha equals to 5%, that means the difference in the sum of squares should be at least 161.45 times greater than the residual sum of squares of the full model, which is quite an extreme criteria. So going back to the picture, we can only reject the null hypothesis if the side DC squared is 161.45 times greater than the square root of AC. That is to say, the triangle ACD should be incredibly flat. So this is all well and good. We have the decision rule, and it is geometrically meaningful. But how do we actually compute these projections? Because it boils down to calculating the projection length squared. Well, we use the standard technique from linear algebra. When we deal with projections and perpendiculars in general, we use an orthonormal basis. This is such a no-brainer in linear algebra. And this is actually close to how least square estimates are done on computers. So it all has to do with the numerical stability of orthonormal bases. So let's calculate the projections. This is purely linear algebraic. Given y as a vector, we want to calculate py onto 1. Because we know the projection of y onto 1 is a multiple of 1. Let's say c times 1 for some c in real. Then by orthogonality, we must have p1y minus y perpendicular to 1. And therefore we can use the orthogonality condition, that is p1y minus y, dot product 1 equals to 0. So here I use the transpose and the matrix multiplication to stand for the dot product. It's the same thing. And this equation can then be expanded to c1 minus 1 prime times 1 equals to 0. Expanding, we get c1 prime 1 minus y prime 1 equals to 0. And therefore c is just y prime 1 over 1 prime 1. And this simplifies to y1 plus y2 plus y3 over 3, which is exactly the average of y. And this is something we already covered in our previous video. The statistic is just geometry. Basically, we showed in that video that taking the average is projecting onto the line spanned by 1. And the standard deviation has to do with the length of the perpendicular relative to 1. Anyway, so this tells us that P1y is y bar times 1, 1, 1. And the P1 perpendicular y is y1 minus y bar, y2 minus y bar, and y3 minus y bar prime. So we need the length squared. So at this point, it's easy to calculate the square length of P1 perpendicular y. And now, given x equals to x1, x2, x3 prime, we wish to calculate the fitted value of the response, mu hat, which is also PMY. We could write mu hat as a basis expansion relative to the basis 1 and x, and then solve for beta 1 hat and beta 0 hat. But remember, these coefficients are irrelevant to our main goal. Namely, we wanted the perpendicular length squared. We at this moment do not care about the estimated coefficients. And also, 1x may not be the best basis for M to work with. We like to work in an orthonormal basis when we calculate projections. The relationship between 1 and x can be arbitrary. There's no a priori reason that 1 and x would be orthogonal. Expanding a vector with respect to an arbitrary basis can be extremely messy. And because traditional treatment of least square regression focuses too much on estimating the slope and intercept in the regression equation, it unavoidably comes with this massive drudgery. It's simply because it's not working in an orthonormal basis. The fundamental object in our consideration is the subspace M. The vectors 1 and x span the subspace M, but it might not be the best basis to work with. Therefore, we completely avoided this messiness. So instead, we construct an orthonormal basis for M using the Gram-Schmidt procedure. E1 is simply the unit vector along the direction 1, and E2 is the perpendicular of x onto the vector 1, normalized, of course. So E1 is 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. The perpendicular of x onto 1 has the same form as the perpendicular of y onto 1. That is x1 minus the average of x, x2 minus x bar, and x3 minus x bar. It's the same algebra as earlier. And after normalizing, we get E2. So mu hat, which is the projection of y onto M, can be now written in an orthonormal expansion, which is much nicer. The orthonormal expansion relative to E1 and E2 is y prime E1 times E1 plus y prime E2 times E2. And the perpendicular of y onto M is y minus y hat. That's the residual vector. And we needed its squared length in the calculation of the F statistic as well. If we really care about the estimated coefficients beta naught and beta 1, let's be honest, they're easier to interpret, but it's no problem. We can recover these coefficients quite nicely from the orthonormal expansions. We have mu hat equals to beta naught hat times 1 plus beta 1 hat times x. We can then expand the vectors 1 and x with respect to the orthonormal basis. So 1 is the square root of 3 times E1. X is once again equal to its orthonormal expansion, x prime E1 times E1 plus x prime E2 times E2. And we substitute these two expansions into the expression for mu hat. So mu hat, after simplifying, becomes beta hat square root of 3 plus beta 1 hat x prime E1 quantity times E1 plus beta 1 hat x prime E2 quantity times E2. And then we can simply compare this expression to the expansion of mu hat relative to the orthonormal basis earlier. Because the expansion is unique, the corresponding coefficient must be the same. Therefore, we have beta hat naught square root of 3 times beta hat 1 x prime E1 equals to y prime E1. That's our first equation. The second equation says beta hat x prime E2 is equal to y prime E2. So beta 1 hat is y prime E2 over x prime E2, and beta naught hat is y prime E1 minus beta 1 hat x prime E1 over the square root of 3. So the idea is we only calculate the coordinates with respect to this arbitrary basis 1 and x at the very end. Whenever there is some sort of orthogonality at play, always work with an orthonormal basis. So this is the numerical example we gave in the beginning. We can carry out the formulas, which I will very quickly go through. So given the data 1, 1, 2, 3, 4, 4, we form the vectors x and y. The vector x is 1, 2, 4, and the vector y is 1, 3, 4. And now we have x bar and y bar equals to these two numbers. This is the perpendicular of x relative to 1. We then calculate this length squared. And this is E1 and E2 obtained from Gram-Schmidt. This is a projection. This is a perpendicular of y relative to 1. That's its squared length. We need this in the F statistic. And now we calculate y prime E1 and y prime E2. This is for calculating the fitted response, mu hat. So mu hat is these two coefficients times E1 and E2 respectively, and we get this vector, which is mu hat. Y minus mu hat gives us the perpendicular of y relative to M, and that's its length squared. And after that's done, we compare the goodness of fit between the full model which is 0.63, and the goodness of fit of the no trend model, 4.67. And the difference is 4.04. The F statistics is this difference divided by the residual sum of squares of the full model. So 4.04 divided by 0.63, which turns out to be 6.41, way smaller than the critical value. Therefore, we fail to reject the null hypothesis at a significance level alpha equals to 5%. And in fact, the p-value, which is the distribution f11 greater than the observed value 6.41, turns out to be roughly 24%. So this p-value is too large. So this tells us that under the assumption of zero trend, observing our F statistic, or anything greater than that, has a roughly 24% probability. So we cannot rule out that the so-called trend in the diagram is simply a fluke. So therefore, we fail to reject H0. And lastly, we can calculate the beta 1 hat and beta 0 hat if we want to. And this turns out to be exactly the same as those numbers in the beginning shown by decimals. This is the least squared line, y equals to 0.50 plus 0.93x. So as promised, this was our visualization in decimals in the beginning. And now we can fully understand what is going on here. The green vector here is the vector 1, 1, 1. The blue vector is the vector x, and these two span this plane, the gray plane, which is our regression subspace M. The red vector, this particular red vector, because in decimal 3D there's not a whole lot of color, so I'm talking about this red vector that is not in the surface, is a y. That vector is a y vector. So we do two projections. One, we project the y vector onto the span of 1. That is this green line here. This green line is in the direction of 1, 1, 1. And then we project the y vector onto the plane and get the purple vector. And in doing so, we create this little right triangle in the space. So now we can clearly see the goodness of fit of the no trend model, the goodness of fit model with trend, the difference in their sum of squares. I apologize if this is a little bit repetitive, but it is really helpful to see this visualization again and again from various angles and perspective to see which vector is the projection of what, and so on. All right, that's it for today's video. Thank you very much for watching, and I'll see you next time. Bye.